Hello, everybody. Welcome to the Global Composite Webinar Series. And my name is Wenbin Yu, the Director of Composite Design and Manufacturing Hub. This webinar series is to examine history, present capabilities, future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 5 decades. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the Composite Design and Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the global community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Solvay, and AnaSwift. We greatly appreciate the financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will last about 45 minutes, and we will have about 10 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. Today, the speaker is from Japan. The time zone difference prevented him from live participation. Well, we will play his pre-recorded presentation especially made for this webinar series. You can still send your questions during the presentation using the Q&A box. After the speaker's presentation, we'll compile your questions and send to the speaker for him to answer you directly. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
Thank you, Dr. Yu. I am delighted to introduce Professor Nobu Takeda. He is currently chairman of the Japan Tech Transport Safety Board and professor emeritus of the University of Tokyo. He graduated from the University of Tokyo with a bachelor's and master's degree in aeronautics, and from the University of Florida with a PhD in engineering mechanics. I first met Nobu in 1981 when he and I attended the first US-Japan conference on composite materials in Tokyo and later Kyoto. His research includes experimental micromechanics of composites and smart composite structural health monitoring and process life cycle monitoring. He's led several Japanese national projects on structural health and process monitoring of aerospace composites, mainly based on optical fiber sensors. He was the president of the International Committee on Composite Materials, the ICCM, from 2015 to 16, and is Japanese representative of the International Committee on Aeronautical Fatigue. He's currently the Asian editor of Composites A, one of our major journals in the field, and he is a World Fellow of ICCM and a Fellow of SAMPI. Dr. Takeda has had over 11,000 citations of his work during his career. His Google Scholar rating is an H index of 58 with an I-10 index of 232. He's had an average citations per year since 2015, almost 750. His most cited paper, The Development of Smart Composite Structures with Small Diameter Fiber Bragg Grating Sensors for Damage Detection, Quantitative Evaluation of Delamination Length in Composite Laminates, has received significant citations since its first publication in 2005. I'm delighted now to turn the floor to the pre-recorded talk by Professor Takeda. Thank you.
And theoretical works. So I'm sort of a man to talk. Today I talk on the fiber optic based in process monitoring technology for shear herpes structures we have been developing for material quality assurance. This slide shows the outlook of commercial aircraft with remaining aircraft in blue and demanded aircraft in red as a function of the year. For larger size aircraft such as Boeing 787, Airbus 350, carbon composite CFRP are widely used as a standard materials for primary structures. On the other hand, for mid-sized aircraft with single aisle and narrow body, aluminum alloy are widely used as a standard materials for primary structures since low-cost, high-rate production CFRP is not available yet. Further technology breakthrough is required to apply CFRP to the next generation aircraft. I mean, replacing these kind of Boeing 787 MAX or A20 Neo, 320 Neo. Although some low-cost, high-rate production manufacturing methods exist using CFRP prepreg, such as AFP and ATL, we still have many manufacturing difficulties in shape distortion and residual stress development during cure and assembly to assure the final material quality. Cure process should be certainly optimized. For example, we have, in such case, distortion called springing phenomena will occur, and during assembly, additional stress will be appear. In some cases, you have a failure there. Or this telescope composite, those cylindrical composite, thick composite, has subject to the residual stress, and then in some cases, crack will be introduced during fabrication. Process simulation code is an effective tool to determine appropriate cure cycle and mold shape with minimum trial and errors. So this kind of code should be properly predict process-induced thermal state, cure reaction, stress or the strain state, and final shape or distortion. This slide shows the challenge of the simulation. Can simulation reproduce actual internal stress or strain state? Input parameters consist of intrinsic ones, such as materials and the thickness, as well as the extrinsic ones, such as true materials on the cure processes. The simulation code is normally validated by comparing the final shape of the manufactured CFP parts after demolding. This validation procedure lacks the knowledge of the internal stress or strain state to clarify the mechanisms of the shape distortion. I believe it is necessary to monitor the internal strain state experimentally using in situ method and to advance simulation by integrating these measured strain values. This is the content of today's presentation on the fiber optic based in situ in process monitoring of the CFP structures for material quality assurance. First, I start with the complete Q simulation scheme, fully integrating internal strain measurement. Then I present some applications in curved composite and the T-joints. This slide shows the deformation during cure process of the SAM setting CFP preplate. Shrinkage after gyration in a transverse direction is important for shape distortion and damage. I'm showing 3 cases here. First one, unidirectional layups with tools, and the unidirectional layup without tool. And the third is the cross-ply layups. The shrinkage consists of the 2 stages. First one is the chemical shrinkage stage and the thermal shrinkage. I'll explain later. We have been developing a method to measure the in situ strain inside the CFP preplate during autoclave manufacturing processes using embedded optical fiber sensors. Composite cure codes are drastically improved with these in situ strain data. This shows a comparison between our proposed scheme here and the conventional approaches. The conventional approaches obtain material parameters through dynamic measurement devices such as TMA, some mechanical analysis, and DMA, dynamic mechanical analysis, to measure cure shrinkage strain and stiffness through the temperature profile at ambient pressure, which is quite different from the actual manufacturing conditions. Validation is only possible with the final shape measurement. Our scheme uses embedded optical fiber sensors during whole manufacturing process. 2 FBG sensors in this case. I will explain what is a FBG sensor later. These 2 sensors are installed to measure the in situ strains in actual and practical autoclave manufacturing conditions. Validation can be possible with internal strains during fabrication and also the final shape. I'm going to show you the principle of the FBG sensors. The structure of the optical fiber sensors is shown in this figure. For example, around 20,000 grating are inscribed in the gauge length of the 10 mm or so of the core to make a FBG sensor. If a broadband wavelength is flat, broadband light guided with the core hit the FBG sensor part, one specific wavelength, lambda b, gets reflected. This lambda b is proportional to the grading period lambda, this lambda, multiplied by the refraction indexes. the shift of the wavelengths, lambda b, can be made by either actual strength or the temperature changes. So if the temperature is constant, the actual strength can be obtained from the measured wavelength shift. FBG sensor can be easily embedded in a silver-B periphery because of their small size and fiber shape, and also the immune to the electrical magnetic interferences. Let me show how to embed an FBG sensor in a thickness direction after the normal layups and vacuum backing. You need some technique, but if you make some practice, you can do it. Sensor extraction areas was flat, confirming minimum disturbance in composite. This illustrates shrinkage measurement, pure shrinkage measurement without mold, using double-sided vacuum backing. Two FBG sensors are embedded into the 90-degree direction. Fiber direction is in this set, in this direction, and embedded into the 90-degree directions. These two sensors have different tail lengths. Tail lengths means the distance between the end and the FBG sensors part. So long-tailed and short-tailed. So two sensors have a different tail lengths, short-tailed and long-tailed. Another short-tailed FBG sensor is embedded in the thickness direction. This shows the high temperature profile, time versus temperatures, heated up and hold it, and temperature decrease. This is the normal autoclave pressure. During this holding time, you can see a chemical shrinkage here. This is the shrinkages. Chemical shrinkage region here. And then after the holding time is finished, you decrease temperatures. During that time, thermal shrinkage can be seen, while the autoclave temperature is lower to the room temperatures. As you can hear, almost same chemical shrinkage strengths are measured for FBG short-tailed sensors in both in-plane and thickness directions, which means that transversely isotropic shrinkage without those mold. If you use the mold instead, you have this day with mold. This is normal cases. Pure shrinkage behavior is different. That is, in-plane strain is highly restricted, but the thickness strain is large, which means transversely anisotropic shrinkage occurs with mold, which is quite different from the transversely isotropic shrinkage without mold. As you notice, we are using two FBG sensors, two different tail lengths with different tail lengths. Measure strain behavior, or I should say, measure strain values, depends on the tail length. So short-tailed and long-tailed, the different strain level is different. Measured strain values depends on the tail length due to the shear lag effect. I hope you are familiar with the shear lag effect. That is strain transfer from composite CFP to the FBG sensors. Strain transfer is sufficient for long tail ones, but insufficient for short tail ones. That is the theory of the shear lag. But this, people know that this strain transfer depends on the local stiffness, especially the shear stiffness of the resin in process. So we propose a method to determine both chemical shrinkage strain and the local modulus of the resin in process by comparing the FEA result you can calculate with compared with the in situ FBG measurement. So FEA was compared with the experiment. Then you can estimate the modulus in process, modulus of the resin in process of the chemical shrinkages during processing. The detail is written in these references. You can consult these our method here. The proposed methodologies can be validated as follows. First, let me show the Young's modulus data of the resin by current method and the conventional DMA measurement. EM versus time, comparing the DMA result with the optical fiber method. The frequency range of the DMA is too high and curing can proceed during the measurement. You can find the Young's modulus data by DMA is rather high compared with the values by the current method. Then, using these data, through the thickness strain in cross-ply specimen is calculated by the FEM analysis using these experimentally obtained parameters. We find these calculated values here. We can find these calculated values closely reproduce the strain measured by the through the thickness sensors. So you can compare with that. This shows the validity of the proposed methodology. Then reliable normal stress in the thickness direction can be also calculated. Now let me move on to the second subject, process-induced strain and the distortion in curved composite. Complex shaped CFP became important part as shown in the top left. This is the Airbus material for the A350. However, process-induced residual deformation occurs in such compressive structures, composite, especially for the L-shaped composite. The angle between the two flanges reduced during curing. The deformation is called spring-in phenomena, and it induces residual stress during assembly. So it is important to actually predict the amount of spring-in to adjust the tool shape. Most simple prediction is proposed by the Radford, assuming the Euler beam analysis. During cure process of the sum setting composite, chemical and thermal shrinkage occurs, and the equation considers both these effects. However, the effect of the thickness cannot be taken into account using this equation. A new idea was proposed based on the shear lag analysis. I think let me show you here the L-shaped ones, which we produced in the lab. This angle should be 90 degrees, but it's very difficult to control these angles during fabrication. Now let me show some of the previous theoretical work by Professor Wisnam of the Bristol on springing phenomena. In their analysis, they consider that the shear deformation is mainly induced by the through thickness shrinkage. When the shear stiffness is low, like early stage of the chemical reaction as shown in the left figure. In this case, insignificant stress is generated and no spring-in occurs. On the other hand, when the shear stiffness is well developed like during cooling, bending moment is induced instead of the shear strain under autoclave pressure. As a result, spring-in occurs when the pressure is released. The situation changes from shear dominant to the bending dominant as cure proceeds. This analysis predicted the effect of the thickness successfully, but we approach this problem with a more experimental and physical point of view as follows. Here you can see the schematic of the specimen and the sensor embedment for the thin 20 ply specimen with the 45 thick specimen fabricated with a cross-ply layouts. And the FPG sensors were diagonally embedded into the plus minus 40 degree directions as shown in these figures. I hope you can see some of the fibers, although this is very thin. These sensors to capture through the thickness shear and normal strain, as I'll show you later. To embed an FPG sensors into the diagonal directions, sensors was cut near the grating area to make it short tail ones. Then hole was made in uncured stacked prepreg using a needle. The depth was controlled so that the grating areas was placed at through the thickness center. Finally, cut FPG sensors was inserted into hole. Basic idea is that through the thickness normal and shear strain, epsilon2 and gamma 1, 2 can be calculated using the plus minus 45 degree direction strains, which can be written like this equation. Summation and subtraction gives a normal shear strain, normal and shear values. We assume that the in-plane strain epsilon1 is negligible because cross-ply layout was used. And this idea is true for composite strain, but shear lag effect needs to be taken into account for the strain in the optical fiber sensors. As I explained before, strain induced in the optical fiber sensors changes along its length due to the shear effect near the fiber end. The strain is written as a product. This measured strain is written as a product of the composite strain and the shear coefficient E, which depends on the composite modulus C and the distance from the fibers L, fiber end, which is called tail length. Then those are introduced. We can get these equations, strain differential in a diagonal sensors. Based on these sensor strains, shear normal strains are evaluated in two ways. First, integrating the summation and the subtraction of the sensor strains gives strains reduced by the shear coefficient written here. Advantage is that the values are separated for normal and shear component, but they are affected by the shear coefficient. The other is the shear normal strain ratio of the summation subtraction. That gives, although this is relative values, the composite strain ratio is directly measured from the sensor strain without any effect of the shear lag. These two values are calculated for thin and thick specimens. I'd like to start with the reduced strain first. Here's a result of the thin specimen, 20 ply specimen. You can see the two values, shear strain and normal strain. Nobody has measured these kind of strains experimentally. The shear and normal strain calculated from the sensor measurement as shown here. And the horizontal axis is time. Left vertical axis is the strain, and the right vertical is the temperature and the strain values. Onset of the strain is set to the gyration point near the 200 minute because the stress is mainly generated after gyration. During chemical shrinkage, both normal and shear strains decreased in the earlier stages, but the shear strain saturated, whereas the normal strain gradually decreased. During cooling after 450 minutes, only normal strain significantly decreased. Normal strain changed from the 1600 to the 1760 micro strain during chemical and thermal shrinkages. Springing angle measured by the 3D scanning was 0.53 degree, relatively large. Then for the thick specimen, during chemical shrinkages, both normal and shear strain decreased gradually and did not saturate it yet. Normal strain was quite larger than the one in the thick specimen, which was 1600. In this case, 33,000. This would be because the sensor in the thick specimen had a longer tail length. And during cooling, only normal strain significantly decreases, same as the thin ones. Moreover, the value was almost same as the thin one, indicating similar phenomena occurred in the thin and thick specimen during cooling period. But in the chemical reaction regions, both are different. Spring-in angle is larger small, 0.38 degree, which is much smaller than that in thin laminates. From the strain monitoring, difference in the spring-in angle would be caused by the chemical shrinkages. Now let me move on to the shear normal strain ratio. This graph shows the shear normal strain ratio calculated by the equation. Since the shear strain was shown to be induced mainly during chemical shrinkages, the figure focuses on the chemical shrinkage areas. These values decreases from these theoretical values pi over 4 just after gyration. This pi over 4 is the theoretical values calculated with a negligible shear stiffness, and it corresponds to the earlier stage of the cure process. This shear normal strain ratio became 0.4 for the thick one, whereas it reached 0.2 in the thin cases. From these results, it was confirmed that the larger shear deformation was induced in the thick specimen, reducing spring-in angle. And then this is an additional figure. This slide shows the effect of the interlaminar layers on the shrinkage strain measured by the 40-degree FBG sensors. FBG started to measure the chemical shrinkage after gyration. Strain changing rate gradually decreased as a cure reaction proceeded. In addition, the additional DMA test confirmed that the TG of the both epoxy resin reached 200 degrees Celsius. I should have explained that this prepreg is used for the Boeing 777. And this one, without these interlaminar toughened regions. In this case, you can see the interlaminar layers with the some plastic particle distributed into the epoxy resin C, I should say. In specimen with the interlaminar layers, shrinkages relaxes here during cure hold compared with these without interlaminar layers, which can be attributed to the viscoelasticity of the some plastic particles. This is TG of the 130 degrees Celsius. Relaxed stress is non-negligible because the vitrified laminate is rather stiff at this stage. In this case, spring-in angle was measured twice, before and after thermal treatment. Shrinkage relaxation occurs, actually affects the final shape. 10% reduction in average here. Angle change is small, but cannot be neglected as the structure must meet tight tolerance. That gives you the difficulty to make those L-shaped ones. in this kind of prepreg. So we have to be very careful about it. Aerospace structure must meet a tight tolerance. Gap fault tolerance is, for example, the 0.25 millimeters. Temperature history differs with part as part, and tool thickness is non-uniform, and each area has a different heating rate and the cure temperature holding time because of the you are using a very big autoclave. So I believe our method is powerful tool for better simulation of the aerospace CFP structures. Now let me show on the cure induced strain and failure in deltoid composite joints. There are lots of composite T-joint structure in current design of the aircraft. T-joint transfer loading between vertical and horizontal panel. This inner part here, called deltoid, which is filled with the CFP prepreg normally. In those deltoid regions, process-induced thermal stress exists, and the initial defect may be induced during manufacturing. Cracks may occur in the deltoid during manufacturing. Now I'm showing here our specimen. Prepreg materials used in this study is the standard materials for the used in the Boeing 777, which is standard material with the interlaminar toughened layers. You should notice there exist different properties in the toughened layer direction and the orthogonal directions. Purpose of the present work is first to understand the stress or strain state in deltoid during cure, and second, understand the interlaminar toughened layer on the deltoid failure. This is a test method. Both skin and the L-shaped part, are crossed by laminates, but 3 different layer patterns are used in the deltoid. Randomly packed, horizontally aligned, and vertically aligned. In this case, we are using a different optical fiber measurement system, which allows to measure the distributed strain along the fiber length with a gauge length of the 2 millimeter. This means you can measure the strain distribution along the optical fiber length. This graph shows the chemical shrinkage strain, thermal strain, shrinkage strain, and total strain in the randomly packed deltoid. You can see the strain gets large towards the bottoms of deltoid. This shows the difference between randomly packed deltoid and horizontally aligned deltoid. Larger strain occurs in horizontal aligned deltoid due to the effect of the toughened layers. Then this shows the difference between randomly packed deltoid and the vertically aligned deltoid. Smaller strain occurs in the vertical aligned deltoid due to the effect of the toughened layers as well. Then all type of deltoid are subject to the cooling test. so that we can introduce the cracking inside the deltoid. The failure temperature is written here, summarized here, where the randomly packed ones are most damage tolerant. The total strain distribution at the failure temperatures are shown in this figure. Almost same strain are obtained in the randomly packed and horizontally deltoid, while the strain is much smaller in the vertical ones. The failure patterns are shown in this figure. Similar failure patterns are observed in the random deltoid and horizontal deltoid, and it seems the strain in the vertical direction is important in the process-induced failure, but the different failure pattern is observed in vertical aligned deltoid. In order to explain the difference of the failure patterns, we conducted an FEM numerical analysis. Calculated two-dimensional strain distribution is shown here. You should see this part in the deltoid region. You can see this stress perpendicular to the top of the deltoid is dominant in this case. And the stress perpendicular to each corner and their magnitude relationship is almost important. However, if we use the stress criteria, normal maximum stress criteria and the transverse maximum principal stress, the maximum stress location and failure location do not match well. Then we consider the energy criteria instead, where the failure index C is shown here. I have no time to explain the detail of this criteria, but the detail can be found in the recent journal of us. And then you can find the maximum value of this location matches well with the experimental failure location. Based on the above findings, we thought that cracking may be suppressed if we use roll structures, as shown in this figure. Actually, we find no cracking even at the minus 180 degrees Celsius. Very damage tolerance in this case. Then we have been very interested in how we can suppress the damage in deltoid and how we can induce crack arresters at the flange skin interfaces. I'll show you some of the results for that. Now I'm showing two ideas for how we can suppress the damage in deltoid. One idea is asymmetric. This is asymmetric lamination of the L-shaped part, although the structure is symmetric, macroscopically symmetric. This part is unsymmetric. This part is asymmetric. But overall, this is symmetric. Decidual deformation after manufacturing can be suppressed in this way. The other idea is the fiber looped deltoid structures. Fiber looped was introduced in addition to the normal preplate. Actually, both ideas work very well. Initial failure load increased by the 3.3% for the asymmetry lamination and by 13.8% for the fiber loop diploid structures. Next, we pursue the idea of the damage tolerance with the crack arrestor concept. Basic concept is a fiber reinforced based crack arresters is shown in this figure. In the adhesive region between these preplate, we introduce the A, zero layer to bridge suppress the cracking opening, and B, 90-degree layer to prevent the breached 0-degree layer from peeling off. Load displacement curve, load versus displacement curve of the double cantilever beam test are shown in this figure. Without arresters, with some kind of arresters, you can see crack is suppressed successfully arrested by the proposed arresters. You can see the internal structures when we use them with the X-ray CT. You can find some of the fiber structure inside using X-ray. Now we introduce crack arrestor concept to the corner of the flange and skin interfaces of T-joints. Arrestor is introduced here. You can find final displacement without arresters, with arresters. You can find the final displacement was greatly improved due to the crack propagation suppression. So we could show the validity of the crack arrestor concept in the deltoids of the T-joint structures. In conclusion, material assurance is a key for more extensive use of the advanced CFOP structures, and the practical in-process monitoring and its modeling is necessary technology for reliable CFOP structures. At the end, now we introduce a crack arrestor. Let me see. Sorry. Today I talked on the in-process monitoring of the CFOP structures for the material quality assurance with embedded optical fiber sensors. These optical fiber sensors, we've been showing this part. These optical fiber sensors can be used in a subsequent component assembly this component assembly, and also in operation, and also during maintenance as well. Monitoring in operation is normally called structural health monitoring. We've been working on this part as well, but we can call whole monitoring system as a life cycle monitoring throughout from the birth to the death of the CFOP structures. We believe this system is most effective for new advanced manufacturing development to create an innovative structure concept. For example, the additive manufacturing is introduced right now, but material quality is a key issue. To make a quality assurance, this kind of technology is necessary for the development. This is the end of my presentation. Thank you very much for your listening. Thank you.
I'd like to thank everyone for their participation today. Again, we thank Professor Takeda for his presentation, pre-recorded here. Excuse me. And we look forward to seeing you again in February as we listen to Professor Carl Schutte on February 24th. I'll remind you to please submit questions to the question and answer box, and we will send those along to Professor Takeda. Please remember to submit a question as a complete question, perhaps with reference to the slide or the topic being queried, so that he will understand that question when he receives it by email, and he will respond directly to you. We will keep this open for the next 5 minutes until noon Eastern to give others an opportunity to enter questions. And again, we thank you for your presentation, for your participation, and look forward to joining with you again in another month to hear Professor Schutte. Thank you.